Howdy folks, it's Dr. Science here again. We're going to be covering now Chapter 2, Biology in Psychology for Intro Psychology. In this section we'll be covering Part 3 and 4 of our Chapter 2 PowerPoints. Part 3 is brain structures. It's a pretty long part, so let's get started. First off, phrenology. Phrenology is an old area of psychology that presented the idea that your mind and your brain has a geography to it, and that the different parts of your brain, different sections of your brain, had different jobs. Just like this meme shows that maybe the part right above your eyes handles memes, and the part down in the back of your head handles movie quotes, phrenology thought that, or proposed that, your brain handled a lot of your personality or different capacities in different sections of your brain. So one of the things, for example, subservience was a pretty big one that they would put out there. Now here's where phrenology goes wrong. Number one, it didn't really have very much evidence behind it, and number two, it was often used to justify slavery in the United States. So folks who studied phrenology would say that the part of the brain dedicated to subservience was larger in African Americans than in Caucasian folks. Now, in all actuality, that's not true. There's no evidence that shows that, and in fact the differences in the way that our brain is wired are greater between any two people than they are between the races or genders or anything like that. That being said, it is true that different parts of the brain handle different parts of your person. So there's parts of your brain that have to do with memory, there's parts of the brain that have to do with understanding visual information, your fear, your reactions to certain things, how you understand different ideas, how you move your foot. So different parts of your brain do handle different jobs, but that personality stuff and the justification of racism is just totally bogus. And of course, in modern psychology, it does not fly at all. So, this next slide is going to give you 4 different groups of structures of the brain. We're going to break down the brain for you in some detail in this chapter. And I don't want to go overboard with all of the information here, but I do want to start presenting it to you. At the top of this slide, you see there's a link to a video. That video is totally optional, but I put it there because it was really helpful. It had some really convenient images that I've used in this PowerPoint, and you'll see them here or there. If you want extra information or someone else to explain the parts of the brain, go ahead and click that video, give it a watch. Okay, so let's start with the old brain, sometimes called the lizard brain. The old brain involves the deepest structures of your brain. So you can see here that it includes the brain stem and some of the parts of your brain that are as far away from your head as humanly possible. They're really deep in there. The old brain, or the lizard brain, handles really basic life functions like having your heart beat or your lungs, or a lot of your organs get handled in there. One interesting fact about the older lizard brain is that people used to believe that the lizard brain, or the old brain, was first to be evolved. We now know that's not actually true. All the different parts of your brain sort of evolved simultaneously, although different species did have more or less use for different parts of the brain depending on what their functions were. So as far back as we can go down our evolutionary heritage, as we can get the oldest brain that we can identify, that we could even still say is a brain, still had pretty much all of these 3 or 4 major sections that we're about to talk to, although they might have looked a little bit differently than they do in our own minds, in our own brains. I need to be careful about that. Okay. Next up, the limbic system, also known as the midbrain. The limbic system handles a lot of mid-tier level thoughts, so things like hunger and fear, stuff that is semi-conscious. You feel fear and you feel hunger, and you can kind of control those, but you also kind of can't. Makes sense that the midbrain would handle that sort of in-between level function. So the old brain, totally unconscious at brain activity. Limbic system, somewhere in between. The cerebral cortex, or the high brain, handles stuff that we are totally conscious about. The cerebral cortex handles your decision making, your personality, your ability to speak and understand language, your ability to understand visual information, your ability to feel. Pretty much all of your senses gets handled by your cerebral cortex, but also your ability to control how you react to things, whether or not you react angrily or in an easygoing way to different things. The last one here on this slide is the corpus callosum. Not always considered a low, mid, or high part of the brain, but it's an important thing in your head. What is the corpus callosum? Well, you may have heard that your brain has a left and right side. That's mostly true for the cerebral cortex. You'll notice that in the limbic system that you can kind of see a bit of a left and right side, but it involves a lot of duplication of structures. And in the old brain, you're so deep into your brain that there really is no need for left and right sides because it's all one thing. So the cerebral cortex has a left and right side to it. The corpus callosum is what connects the left and right side, and we'll actually see in a picture that the corpus callosum is kind of the switchboard for your brain. It allows for the connections between all of the different brain structures, so it's super important. An interesting thing about the corpus callosum is that it allows for the cross-wiring that our brains and bodies have. Now, what does that mean? It turns out that the left side of our brain handles the right side of our bodies. You may have heard that before, but what you might not have heard of before is the why. So ask yourself, why would it be beneficial, evolutionarily, for the left side of our brain to handle the right side of our body and vice versa? I'll give you a hint. Part of the reason that the oldest brain is in the deepest part of your head is so that it's the safest out of all of the brain structures. It's pretty dang hard to damage the old brain just by getting hit or stabbed or somehow, because it's so deep in your head. And the reason it's important that the old brain is kept the safest is because it handles the most basic life functions. This is why some really traumatic brain injury can cause you to go into a coma where you no longer have higher order functions and maybe not even mid order functions, but you're still kept alive by this old brain that was kept safe and in the deepest part of your head. So going back to this question, why would it be beneficial for cross-wiring, for the left side of your brain to handle the right side of your body and vice versa? I'll give you to the count of 3, so if you'd like to think about it, go ahead and pause. 3, 2, 1. Okay, well, there's no perfect answer to this because as psychologists and as scientists, a lot of our job is to kind of archaeologize what evolution has done for us. But one thing that we can say is that the cross-wiring of our brain and body allows us to stay safe. What do I mean? Well, let's say that you get attacked by a bear on the right side of your body, and the bear hits the right side of your head. You still need to be able to push the attacker away, hit it, or drag yourself away. And so if the right side of your head gets hit, the right side of your body is still perfectly functional because the left side of the brain handles it. By cross-wiring the brain and body's connections, we are kind of making sure that we're never up a creek without a paddle, because we'll always be able to make those split moment reactions despite having been hit in the head on that potentially dangerous side. I hope that makes sense. I kind of feel like I flubbed the description there, but let's go ahead and move on. Feel free to send me an email, ask questions, and I'll try and explain it a little bit better for you. So we're going to go through each one of these structures in a little bit more deeper context, but I'm not requiring you to learn all the individual structures of these sections of the brain. I'm just going to introduce them to you. Watch out for things that have these underlines though, because you are going to be responsible for those underlined ones, their vocabulary. Okay, so the old brain structures. Let's start from the top left. the thalamus. So the thalamus handles sensory information related to seeing, hearing, touching, and tasting. The reticular formation down here is the network inside the brainstem that's essential for arousal. So arousal in this case meaning getting ready to get up and move around. The medulla automatically controls the beating of hearts and beating of lungs. And you'll notice that this, the most basic of basic structures, is in the most deepest of deepest places in your brain, down in your brain stem. The pons helps coordinate several other automatic functions, pretty much directly connected to the medulla. The brainstem, ancient and central core of the brain, not a big surprise. The cerebellum here is my favorite part of the old brain, and I think it's the most interesting. The cerebellum is responsible for handling a lot of automatic functions that you learn over time, as well as a lot of automatic things that can happen without your learning them. So, for example, if you've ever heard of the phrase muscle memory, the cerebellum is actually where that muscle memory gets developed. It's where automatic movements of your body get learned and stored. So think about this. Try snapping your fingers. Did you really think about what you did to make that snap happen? Or did it happen automatically once you decided to snap your fingers? More than likely it was an automatic movement, and the cerebellum is responsible for that automatic movement. Now, think back to when you were learning to snap your fingers. You really had to do everything on purpose, and it was slow and awkward. When it was that slow, awkward, purposeful movement, the cerebral cortex handled it. The cerebral cortex is a slower, higher order of brain function, or a set of brain structures that handles that purposeful stuff. But as you get better at something and as you practice it, the cerebellum is going to pick it up and let it become automatic for you. This slide here just says that the cerebellum is responsible for nonverbal learning and memory, the perception of time, and modulating emotions. Like I said, muscle memory is pretty dang important for the cerebellum. Modulating emotions is another one that might be interesting for you. So if you are someone who has trouble controlling your emotions, you may have been told that controlling your emotions is actually a habitual thing. And we can actually show that because the cerebellum is such a big part of controlling your emotions, and we know the cerebellum handles automatic stuff. Putting those two pieces of information together should tell you that as you control your emotions more on purpose, you gain practice doing it, and after some period of time, that emotional control happens automatically. Now, I'm not saying that emotional control is the best or worst thing to do. There are some cases when controlling your emotions is a good thing. Like when you're dealing with children, you don't want to let yourself get angry easily. It can be a bad thing too. You don't want to get yourself to a point where you're incapable of crying, for example, which is actually a really great thing that lets you free a lot of the trauma that you're experiencing. So controlling your emotions can be good and bad. You want to have a little bit of a middle of the line thing there, but it's so cool that that emotional control is handled by the cerebellum, an old brain structure that handles automatic activity. Okay, we're not going to spend that much time on the limbic system, in reality because I don't like it that much, but let's go through the structures there. The hypothalamus regulates body temperature, circadian rhythms, which is your body's clock, like waking up and going to sleep. Hunger helps govern the endocrine system. We already talked about the endocrine system just a little bit, and you'll notice down here one of the glands that we talked about is visible. Do you remember what it was? I'll let you double check on that on your own. The amygdala, named the name amygdala kind of comes from the Greek word for almond because it is kind of almond shaped. In this case they say it's lima bean shaped clusters of neurons. The amygdala is famous for handling fear and emotions. And it says here that the amygdala is involved in memory consolidation and emotion. What memory consolidation means is turning information from a direct recording of what happened into a memory that is more concentrated and useful. Now, the fact that the amygdala handles emotion and memory should tell you a little bit about how our memory works. Some of our most important memories are going to be those that are riddled with emotions, and that's not a surprise because the same structure handles both things. Fear is a big thing in the amygdala, so it's not a surprise too that our learning comes in no small part due to fear or other emotions. Okay, hippocampus, central to learning and memory. The hippocampus is a structure that we are learning a lot more about as we have more sophisticated psychological tools, but it has a lot to do with converting memories from your short-term to your long-term memory, and that's kind of easy to remember because hippocampus kind of sounds like the campus of your college, so it's easy to remember that one. However, you don't need to know any of these three structures as long as you know that the limbic system is your midbrain and and you have some vague idea of what the midbrain does, you're Gucci. Okay, the cerebral cortex. The cerebral cortex is one that I will require you to remember pretty well. Cerebral cortex is made up of 4 different lobes. The frontal lobes, and they're plural because you have the left and right frontal lobe, temporal lobe, occipital lobe, parietal lobe. The next slide I've got here has a little bit of a better description of what those lobes do for you. So the frontal lobe, located in the front of your head, handles planning of movements, mental and emotional control, inhibiting unwanted behavior. I've got little mnemonics to help you remember what each one of these does. So the frontal lobe, in my head, I think about it as the front desk lobe. So a lot of control and triage of information. Next, the parietal lobe, this kind of top back one here. Parietal lobe is all about your sense of touch. It's also about controlling your physicality and movement. So the way to remember that one is that P, parietal, is kind of a soft sound, and so it might be easy to remember that parietal has to do with touch because it's a soft sort of sound. I don't know if that works for you. Kind of the p sounds like someone tapping on the table. That's kind of the weakest mnemonic I've got on here. The other ones are a little bit better. The cerebellum I've included here, like I said, because I like it quite a bit. It handles automatic physical motion and learning. You can see the cerebellum right there. The mnemonic I've got for you there is Miss Bellum. I don't know if you've ever seen the Powerpuff Girls. It was pretty successful and interesting cartoon that was available on Cartoon Network when I was younger, and there was this secretary there, Miss Bellum. She was the secretary for the town mayor in that show, and the thing about Miss Bellum is that she really handled just about everything because the mayor was kind of a dummy. So all of the day-to-day activities that the town needed to be controlled were handled by Miss Bellum. So in my head, it's easy to remember that the cerebellum handles that automatic stuff. Okay, the occipital lobe, here in purple at the back of your head, handles visual information and processing visual stuff. Much like in the previous the sections, it's not a surprise that the occipital lobe is in the back of your head because it's the furthest away from your eyes. So if you get hit in the front of your head, your ability to process visual information is still totally safe. Alternatively, if you fall backwards and you hit the back of your head, your vision might go dark, your vision might get blurred, but your eyes will still be perfectly safe, and so you'll still have some ability to see, probably after at least a moment or so. Okay, last one, temporal lobe. Oh, sorry, the the mnemonic for occipital lobe, that one's really, really easy. It's the ocular lobe, occipital ocular, not too hard of a leap there. Finally, the temporal lobe, kind of on the sides of your head, located pretty close to your ears. Your temporal lobes handle hearing and language and understanding written language. So this understanding vision has a lot to do with understanding that written language stuff. And temporal lobe, unsurprisingly, is pretty dang close to your ears. The mnemonic for remember what the temporal lobe does is that it's the tempo lobe. Tempo referencing music, right? So that one should be pretty easy. You are responsible for each one of these lobes plus the cerebellum. So make sure they make sense. And if you need to come up with your own mnemonics, let me know what they are, and I might include them in future classes. Now, we've talked about the way in which your brain is divided up into structures, and those different structures handling different jobs. We've talked about a lot of those different jobs, but I'd like to bring your attention to the way that the brain kind of divides itself. We can divide the brain based off of our own understanding of how it works, but notice all these folds that the brain has. Notice that the temporal lobe is really clearly separated from the frontal and parietal lobes. A little bit less clearly from the occipital. The frontal lobe kind of has a pretty clear fold going up to the parietal lobe. The occipital lobe pretty clearly separated from the parietal lobe. These folds have a major purpose. They allow for your brain to have a really sizable surface area. The surface area allows your brain to be based on connections instead of just kind of a big soup. The reason those connections are important is something we learned in the previous video. It's because the connections are what makes your brain function. Let's take a look at one subsection of the parietal and frontal lobes known as the motor cortex and the somatosensory cortexes. I teach these because I find them to be interesting and exciting, and they really do a great job of showing, again, how the different brain parts handle different jobs. So the motor cortex and somatosensory cortex are located kind of right on that border between the frontal and parietal lobes. So if I pop back over here, there are these kind of sections right here, these pretty clearly delineated sets of wrinkles. And the motor cortex handles controlling movement of your limbs, all the stuff that you consciously, purposely control. And the somatosensory cortex handles the sensations coming from those limbs. So the feeling in your hands and feet and lips and legs and all the other feelings that you possibly have. Now notice that your body is kind of represented roughly in the same way that your body actually exists. It's represented kind of the same way that your brain, that your body exists in the brain. So here we have part of the motor cortex handles toes, ankles, knees, hips, the trunk, which is kind of from thigh up to your torso, arm and wrist, fingers and thumb. And the reason these pictures are kind of done in this wonky sort of way is to show how the larger parts of your brain are associated to more important parts of the motor or sensory function. So your thumb is a very dexterous and precise finger, and therefore it's got a larger part of the motor cortex associated to it, as well as a larger part of the somatosensory cortex. You'll notice that the somatosensory cortex has a lot of feeling for your jaw, but your jaw doesn't really have that much of a motor component to it, because, well, you can really only do a couple of different motions with your jaw, and your chin doesn't really do anything. It doesn't have an ability to move, so there isn't a motor cortex part associated just with the jaw. That being said, you can see over here that swallowing, something that isn't super felt when you do it, you don't really feel that much swallowing, has a part in the motor cortex because we can purposefully control that swallowing action. Another cool thing about this picture is that it really clearly shows where the connections of your brain start versus the cerebral cortex. So this colored part on both of these pictures is the cerebral cortex, and this stuff here are connections that allow information to go from different parts of your brain, and this is kind of the edge of the corpus callosum. Here we've got another picture that shows sort of the same bits of information, just in a different way for you. Feel free to take a look at this in more detail, but the thing I want you to take away from this is this new word here, the sensory, motor, or cortical homunculus. Homunculus is going to be the vocab term. He kind of goes by a couple of different names, as you can see here. Homunculus is a word that just means the little man in your head. And so if you think about this motor and somatosensory cortex layout geography, it does kind of have a little bit of a little man thing going on. Now, if you think about how your mind works, a lot of people like to think about the mind as being just a little guy or a little girl in your head. Now, there isn't actually a person in your head, but these representations of your body could be considered a little person or a homunculus. There's a cool figurine that gets made out of that homunculus, and that's these two dudes here. The sensory and motor ones are different, and that's because there are different relative sizes of your body proportions for your sensory versus motor parts of your body, or sorry, sensory versus motor cortexes. You can kind of look at these and feel for yourself around your body whether or not they're totally true or not. Some of these things are a little bit more or less accurate given the fact that, well, they needed to have made the doll so it could stand, so maybe the legs are not the correct portions. But the head and hands are the ones that are really obviously proportionated to be roughly the size that they actually take up in your brain. You'll notice that hands are super, super important in the motor model because we have a lot of control in our hands. But the legs in the motor model are just a little bit smaller than the legs in the sensory model because we don't have like as much sensation in our legs. So not that huge of a surprise here and there. One thing that is, there's a couple things that are kind of wrong. You really don't have that much sensation or control in your eyes, but the head needs to be big, so the jaw and the lips are kind of huge because you do have a lot more sensation and control for those. Another thing that's kind of janky here is that the genitalia should be pretty dang huge in the sensory model and pretty dang non-existent in the motor model because you don't really have that much control over your genitalia. That being said, they didn't do that because that would be kind of gross. So there you go. Okay, so remember I was talking about the folds in your brain. Those folds have names. You're not responsible for learning those names, but I just wanted you to know that they have names. The upwards folds are called gyrus or gyri, and the downwards folds are called sulcus or sulci. And if you want to learn a little bit more about what those wrinkles or folds do, there's a nice website here that'll teach you more about it. Suffice to say that the brain needs to be folded to give it kind of more area for more individualized jobs instead of having just a thicker part of the brain and the neurons can figure out what parts they are for there. So the folds are kind of one way that the brain organizes itself. And you'll notice that the folds are pretty inconsistent across most brains. I misspoke a little bit there. There are folds in your brain that are consistent across different people. Not all of them are consistent, but the major ones are pretty consistent. So the division here between your temporal and frontal lobe are pretty dang consistent across different people, but there might be slight differences, especially in these more smaller folds or doodads and thingies. Sorry, I'm kind of going overboard there. Here's a little bit more visual information on the corpus callosum. Here you can see, just like we saw previously, how the different left and right sides of your brain are connected up, down, through the corpus callosum. So the corpus callosum is really this middle structure here, but it's got kind of this cauliflower thing going on where it hooks up to all the different parts of your cerebral cortex. Now, to show you the importance of the folds of the brain, you can see that a mouse brain here has very few, if any, folds to it, but our brains are a lot more complicated than mice brains, and therefore they've developed these more complicated geometric structures or geographic structures. Fun fact, over time the human brain is actually getting smaller, and this is because it is becoming more efficient. You would imagine that a bigger brain might be smarter, but that's actually the opposite of true. Why would a smaller brain be smarter? Why? This actually lines up too with women having smaller brains and being, on average, a little bit smarter than men. And what's going on there is actually that the brain has to send signals through itself, right? And those signals take time. The smaller and more complex the brain, the faster it can transmit information from one side to the other. So the reason the brain is getting smaller, not just because, in part, is because we are getting more efficient. We don't need as much space to accomplish the same thing. Another reason it's getting smaller is because as we evolve as a species, we are constantly evolving. We're actually evolving brains that require less energy. The smaller they are, the more efficient they are, the less energy they require, and the better we are equipped for survival. Again, those are things that you really don't need to know, but I'm just trying to give you more information to help you along. Maybe one of those things will be interesting and exciting to you. Here's a website where you can learn just a little bit more about the wrinkles in your brain. Here's another set of pictures to show here the corpus callosum in a real brain here. It looks kind of black in different parts because it's been manipulated to keep it together. The brain itself is pretty soft and gelatin-like, so it can be easily damaged, and it starts to decay fastest out of any of your body structures. So they need to manipulate it. They have to fill it with chemicals in order to keep it consistent. But looking at this slice of the brain is pretty interesting because you can see not just the corpus callosum, but you can see here the brainstem, medulla, the gland that we were talking about. Do you remember which one that was? The cerebellum. And we can talk more about this in length here, but that's pretty cool. This is a computer visualized version of the cerebellum and its connections to the different parts of the brain. The way these are color-coded is kind of, I'm not sure exactly how they're color-coded, but it's probably one of two things. Number one, how much activity is in those different parts. So the corpus callosum is red because there's a lot of activity going on there. Another way this might be coded is to show the connection. So the same colors react to the other colors. So that there's some red stuff here that goes through the corpus callosum and comes out in all these other little red branches. Sorry I don't know more about this, but I think it's a pretty interesting visualization to show the corpus callosum as well as all of those little branches of connections in there. Okay, so here we've got a video. I think this video is pretty interesting. In class I would show maybe just a part of it, but the cool thing about this video is that it shows what happens to you when you do not have information coming into your brain, into your mind. Your brain actually starts to look for information. Your neurons constantly fire. They fire once every couple of seconds. And if they are not receiving stimulation, they get bored and start to make stuff up. This is why being in a sensory deprivation chamber can make you hallucinate. So if you'd like, go ahead and give a watch to this video. I'll count down 3 seconds to give you that chance. 3, 2, 1. Okay, so this next slide is an interesting story, one of the most famous stories in psychology. I would be a terrible intro psych teacher if I didn't present this story to you. This is the story of Phineas Gage, presented here in video format for you. If you'd like to watch that, I'll give you the quick and dirty on Phineas Gage verbally for you right now. Phineas Gage was a man who worked as a railroad, I think he was called a tamper. a long time ago, when they were making railroads, they used gunpowder to explode holes where they could then drive metal down into the earth and affix railroads to the ground so they would be totally steady. Now we've got machines that do that for us, but back in the day there were people who needed to drill a hole, and then people who would put the gunpowder in there and squish it down with a metal rod. And so that squishing down and pouring of gunpowder was Phineas Gage's job, and he was actually pretty good at his job. He worked really hard, and he was a really steady man. However, unfortunately, one day when he was working, he kind of had his head above the hole that he was filling and tamping with gunpowder, and that caused an explosion, and that caused this metal rod to shoot straight through his head, going through kind of this upper jaw, right behind his eye and out the top of his head, really went straight through his frontal lobe. You can see here that his left eye was permanently damaged. But the man survived. Here's his skull, kept for posterity and kept for further research. Phineas Gage survived having a giant metal rod rammed straight through his head. The thing landed, I think it was 30 or 40 feet away. And the strangest thing was that he was able to literally walk himself to the doctor. Now, this is a huge bit of brain damage that happened to this man. So what happened to him? He couldn't have come away totally unscathed. Well, here's a visual image that kind of shows what might have happened to him. This is actually from a different man who, let's see, lost part of his left frontal lobe. And something similar to Phineas Gage happened to this man. So in this guy, he became more impulsive and killed the deputy sheriff. 19 years later, he was executed for his crime. Phineas Gage also became more impulsive. People say that he was no longer the same person. His personality changed overnight. He became an angry drunkard, and he was no longer capable of controlling himself or his emotions. And remember, the frontal lobe has a lot of that decision-making job, so it's not a huge surprise that damage to your frontal lobe could change your personality that drastically, could reduce your ability to make intelligent judgments. I wonder if it went through any of the mid-brain. Probably none of the old brain, but maybe some of the midbrain. I'm not sure. Okay, so you may have heard that I'm pretty sure I talked about this girl in most of my classes. This is a case of a girl who had some pretty bad seizures, and they needed to remove almost the entire left side of her brain. However, she was able to survive, and she was actually able to relearn how to move her body thanks to the compensation going on through neuroplasticity. That being said, her personality, her memory, a lot of things changed pretty extensively, at least for a short period of time, while her plasticity allowed her to recover. Apparently she lived a pretty dang great life. This seems to be from 2008-2013, so I wonder if this lady is still, kicking. I'm not sure. Okay, different types of neuroimaging. These are different ways that we can get visual information about your brain. Again, you're not responsible for all of these, but I just want to present them to you so that you might have some awareness of them. Here we've got 4 different types of neuroimaging. The first is EEG, electroencephalography. Try saying that one. Try reading it without just copying what I just said. Electroencephalography is a type of neuroimaging that involves reading electrical signals coming from your brain. It uses, kind of reads a lot of the magnetic stuff going on there, and EEGs are going to be the type of neuroimaging that is most closely associated to reading brain waves. This is the output you get from an EEG, and you can kind of see the brain waves there. EEG is most used for cerebral cortex jobs because it's pretty dang impossible to get a read on some of the deeper brain functions with EEG. Okay, PET, positron emission tomography. It's a type of neuroimaging that involves drinking a solution that is radioactive. Now, it's just a little bit radioactive. It won't hurt you, but what it will do is send out these positrons that the machine can then read. And the reason it is beneficial is because your brain uses more or less blood, receives more or less blood, depending on which part of the brain is active. So if you're really looking at something and trying to decipher that visual information, the occipital lobe will be using more blood, and so we'll see more radiation, versus if you're trying to really think about a decision, maybe your frontal lobe will do different things. So it's that combination of sugar going to your bloodstream going to the active part of your brain, and then we read the active part of your brain via the positrons being emitted by the radioactive substance in your blood. Okay. MRI, magnetic resonance imaging, does something similar to positron emission tomography, but in this case, magnets are reading the blood and structures of your brain. MRI scans are most often used in medical settings to get a visual picture of what's going on there. They're not super useful in psychology, but they can show if you have like a if you have a tumor or something like that in your brain. fMRI is a special type of magnetic resonance imaging. It's a functional magnetic resonance imaging, and the difference is that it's a bit of a live picture, so it can show which parts of your brain are active at any given moment. Once again, fMRI has all to do with which parts of your brain have more or less blood in them. If you look at these blue and red splotches, usually the way fMRIs are read, as well as PETs, is by concentrations and relative activity. So this blue part of the brain is less active than average, the red part of the brain more active than average. So you have to get a baseline with fMRI, and it's only as fast as the speed that your blood moves around, but it's still a very useful technology that can teach us a little bit about what your brain is doing at any given moment. Here's another picture of an fMRI, this time from the side. Looks like this person is processing some visual information. Let's see what this caption says. As the person looks at a photo, the fMRI, functional MRI scan, shows increased activity in the visual cortex of the occipital lobes. The person stops looking and the region instantly calms down. So there, I was able to guess that this person was processing visual information because the occipital lobe was lit up here. So that's not just because I know this picture. I don't actually remember putting this slide together, but that's because I did this a couple weeks ago. Okay, part 4, consciousness. We've kind of talked about consciousness at the beginning of this chapter, and now I want to talk about some more concrete aspects of your consciousness. So this is the last part. Let's get going. What is consciousness? That's an interesting question. Not that many people tend to think about what consciousness is. At the beginning of the chapter, we talked about your mind being indivisible, and so folks oftentimes will say that their consciousness is one thing. But I've already proved to you that your consciousness has separate parts. Another way I can prove to you your consciousness has separate parts is, well, you have a sense of location for a lot of the things that you think and feel. So if you touch your foot, you are conscious that the feeling is happening where your foot is, not kind of all over your body or in your mind. And if you have a feeling of hunger or anger or sadness, emotions tend to have a location in your body, and it's not always in your mind. Extreme sadness definitely gets felt in your chest. It feels like your heart's getting squeezed, right? So consciousness is an interesting thing. Another thing I'd like to propose here is the idea of varying levels of sentience or aliveness. So we know that rocks are not alive, and we know that people are definitely alive, but it's an interesting notion to think of how single-cell organisms or microbes might be a little bit more alive than rocks, and just a little bit less alive than plants, moving up to bugs, avian, animals, mammals, and even babies you could consider might be a little bit less conscious of the world around them than fully grown adults. Consciousness is an interesting and confusing and exciting thing, and we can talk about it forever, but instead I'd like to give you the opportunity to watch this video. If you just want to watch the minimum, I would watch at least until the introductory little song and dance starts, but it does a great job of presenting the idea of consciousness and asking you some interesting questions. This is by a YouTube channel named shoot, it's hard to say. It's like Kazurgastat or something like that. They do lots of really great explanations, and they are consistently backed by science. So feel free to take a look at part or whole of that video, and I'll give you 3 seconds to do it. So go ahead and pause this one. 3, 2, 1. Okay, hopefully you found that interesting and exciting. Oh, I definitely know that I've mentioned in all my classes the idea of the location of the soul. So there's really no location in the brain for the soul as far as we know, but people used to think that it was in the pineal gland. We've already kind of talked about this. Located right there. Right there. Isn't that exciting? And it's kind of cool that people used to think that it had to do with the soul, because the pineal gland has a lot to do with your sleeping and waking cycle. Okay, so let's talk about the left and the right side of your brain. Is there such a thing as left versus right-brained people? Well, there's really no good answer to that. The left and right sides of your brain handle different jobs, and so depending on what the job is, the left or right side of the brain might be more or less active. And also, just depending on where you live and your genes, you might favor the left and right sides of your brain. Even just being left or right-handed can be an indicator of what side of your brain you favor. But I really want to present the idea that the left and right being a left or versus right brain person is a little bit more complicated than simply a yes or no answer. This video is really cute, it's kind of short, and it does a great job of presenting what the left versus right side of the brain does, as well as how it relates to different people. I really encourage you to give this one a bit of a watch. When I show it in class, I plan to show it until this image comes up, so go ahead and give that one a watch. Maybe I'd show the whole thing, I don't remember how long it is, but let me give you 3 seconds to do that now. 3, 2, 1. Okay, so next slide about the left and right side of your brain. Remember that we have this cross brain wiring going on. Not only does the left side of your brain handle the right side of your body and vice versa, but also your vision is also left and right side kind of coded. So the left visual field, stuff that is on kind of the middle to the left of your vision, is handled by the right side of your brain, whereas the right visual field is handled by the left side of your brain. Why would the body be switched up like this? Well, I've already given you a couple examples of different reasons why this thing might happen, so I'm not going to go over it again, but feel free to give this a thought and let me know what you come up with. Okay. Another thing to point out is the topic of split brains or split brain people. When folks have a major problem in their brain, most often seizures, one way to solve that, kind of a last option, is to cut the brain in half. Now, they cut it by simply slicing the corpus callosum, so the left and right sides of the brain are no longer able to directly interact. There's a cool video here that talks a little bit about that, and another video here that shows you what goes on when that happens. So I really encourage you to watch these videos and get a better idea of what happens when you cut the left versus right side of the brain. Once again, I'll give you a moment to do that. 3, 2, 1. And if for whatever reason you need to type these videos in, I'll give you a 3, 2, 1. But I don't know how you've been getting to the video so far, but I really encourage you to just download the PowerPoints and click on the links. Okay, new topic in consciousness, and this is something you do need to know. It's got that underline, meaning that it's vocabulary. This topic is the topic of selective attention. We've already kind of talked about this a little bit, but we haven't talked about it using our official terminology. Selective attention is how your brain notices or ignores certain pieces of information. Go ahead and click on this link and give this video a watch. It does a great job of showing you selective attention and how, depending on what you're paying attention to or what you're looking for, you'll hear, see, taste, notice different pieces of information. Here's your 3 seconds. 3, 2, 1. So it may feel as though we're aware of everything that's going on around us at every moment, but that's just not true. In fact, our brains cannot process all of that information despite being as complicated as they are. Instead, our consciousness makes us feel like we're processing everything going on around us, when in actuality we're just ignoring a lot of those things, and because our brain is ignoring them, they're not part of our consciousness, so it doesn't feel like we're missing out on information. When we ignore something, we experience inattentional blindness. Inattentional blindness is where we don't perceive something because we weren't paying attention to it. Pretty straightforward thing. Selective attention and inattentional blindness are very, very similar sorts of things. Selective attention is just our ability to choose what we pay attention to. Inattentional blindness is how we are blind or unaware of the things that we're not paying attention to. Here's another video that was pretty famous thanks to a certain daytime television host. I'm forgetting what her name was in this moment. Shoot, I don't remember. But it does a great job of showing the same attentional blindness or inattentional blindness thing going on. Next up, another video that I really, really love. This is by a magician, and his whole deal is that he's actually not so much of a magician, he's more of a pickpocket. So he does a lot of things that abuse your selective attention. If you skip out on videos often, this is one that I really, really encourage you watch. In addition to this one, they're all just wonderful, and they do a great job of showing you how, despite how you might think you're noticing everything around you, you really are noticing very little. This is a video that I try to show all of my psych classes, even if it doesn't make sense. I love this guy, Apollo Robbins, and he does some great work, and he's just a really good showman. Okay, are we completely unconscious? So let's talk about sleep for a little moment. Are we completely unconscious when we're asleep? Well, are you totally unconscious when you're asleep? What do you think? What do you think is the purpose of sleep? We've talked about a couple purposes. What happens to us if we don't sleep? Let me give you a brief answer from my own perspective for each one of these questions, but I'd really like you to have the opportunity to think of answers on your own. So I'll give you 3 seconds to pause the video. 3, 2, 1. So, are we completely unconscious when we are asleep? The answer is no, and yes, mostly no. So, we have different stages of sleep, and we become more and less conscious of the world around us depending on how deep a stage of sleep we're in. That being said, regardless of how deep of a stage of sleep we're in, we're always going to be conscious. If someone screams at us, if a loud noise happens, if someone taps us, if we smell something really gross, we'll wake up. So we're not totally unconscious, but we are less conscious than we are when we're awake. What is the purpose of sleep? Well, there's a lot of different purposes for sleep. There's not really any one good answer. We've mentioned that it allows you to clean up the neurotransmitters in your brain. We've mentioned that it allows you to solidify memories and get rid of the memories that aren't very interesting or useful. Sleep also gives your body an opportunity to refresh itself and grow and become stronger. So when you exercise, your muscles repair themselves and get stronger when you are sleeping. So if you're ever trying to work out and get more buff, remember that sleep is an important part of becoming stronger too. What happens if we don't sleep? Well, that starts to get a little bit hairy, and there is a scary disease where you can no longer fall asleep no matter what you do. So what happens if we don't sleep? Well, there's a lot of different things that happen. Our body is deprived of its natural opportunity to refresh itself, and our mind starts to decay because it is not given the opportunity to refresh itself. Our neurotransmitters get to the point where they sorry, excuse me, our neurotransmitters get to the point where they haven't given had the opportunity to replenish themselves. Our neurons don't have as much of a chance to grow. If we don't sleep, we start to experience hallucinations. We get dumber, and eventually, if we don't sleep for a long period of time, our body starts to shut down and we can die. So that's really unfortunate. Fortunately, it's pretty hard to avoid sleep. If you manage to stay awake for a couple of days, there will be a point where your body just straight up knocks you out because you are killing yourself. So make sure make sure to get a good amount of sleep. Remember, more sleep tends to be better, but probably the best thing for you is to get consistent sleep. Try and sleep in a consistent schedule. Inconsistent sleep schedules can cause some of the same symptoms as not sleeping enough, so watch out for that. Okay, so the stages of sleep that I mentioned previously can be divided up into a bit of a sleep process. So you don't need to know all of these stages, you don't need to know the whole process, but I'd like you to be aware of kind of the major ideas here. So how does sleep happen? First, signals in the world make you want to go to sleep. When the sun goes down, your body perceives that and starts to send out hormones that make you want to go to sleep. Neurotransmitters and hormones that make you want to go to sleep. Sometimes eating can do something similar. Laying down and being calm can do something similar. And there are certain things like white noise that can help us get there as well. Next, we go into some of the higher sleep stages. We start at sleep stage 1, move to 2, 3, and then get to REM sleep. Sleep stages 1 to 3 involve a lot of sort of half awakeness, especially sleep stage 1 and 2. So if you've ever been falling asleep but still been kind of aware, you're probably in sleep stage 1. So that's when, say, you can't sleep but you're lying perfectly still and you're just mostly listening to an audio podcast or the rain or something like that. It's pretty easy to fall asleep when you're in sleep stage 1. It's very much a transitional period. Sleep stage 1 and 2, if you've ever been falling asleep and suddenly jolted yourself awake, what's going on there is actually your heart is slowing down for sleep, and it's slowing down at a rate that is so quick that your brain goes, uh-oh, we might be dying, and it gives you a jolt of adrenaline to wake you up and get your heart pumping again. That's actually your brain trying to keep you alive and making the mistake in not realizing that you're falling asleep. What's going on there is you're falling asleep so quick that your brain gets scared that you might be dying. So thanks, brain. Sorta. You're trying. Okay, REM sleep. REM sleep is the deepest type of sleep, and it's also the most important type of sleep. It's called REM sleep because it stands for Rapid Eye Movement Sleep. And so when you're in that deepest stage of sleep, your eyes actually start to jitter around really rapidly. REM sleep is responsible for your dreaming, and so even if you don't remember dreaming, almost everybody dreams, and if you do get a good night's sleep, you will dream, even if you don't remember it. Part of the reason that it's hard to remember your dreams is because sleeping involves the consolidation and the removal of useless information from your memory, right? So you kind of have this active process of forgetting when you're asleep, so remembering a dream, it might be a little bit counterintuitive to what your brain is doing at the time when it was dreaming. Lastly, we've got waking up, which is kind of a process that reverses. Ideally, what goes on when you sleep is you cycle through the sleep stages 1, 2, 3 REM, 1, 2, 3 REM. Those cycles tend to last about 90 minutes. So if you ever need to take a really a strong power nap, or need to sleep for a limited amount of time, try to sleep for 90 minutes. Or if you want to sleep more than that, sleep for 180 minutes. Or more than that, sleep for 270 minutes. When you naturally wake up, that is a function of your natural sleep cycles bringing you up to higher levels of sleep and out to the point where you could wake up. If you wake up in a jarring way, like you have an alarm, you'll notice that sometimes when you wake up, it's hard to wake up, or it can be even painful or stressful to wake up. That's because you're yanking yourself out of some of the deeper stages of sleep, and it's not so good. Another thing about sleep is that snoozing, hitting the snooze button on your alarm, is also not very good because it's confusing to your body. When you hit that snooze button, you wake up and try to fall asleep again. Most snooze buttons are 5 to 10 minutes, so that's not enough to achieve one of these sleep stages. So really all that's going on is that you're making yourself try to fall asleep again, and just as you're getting to the point where you're falling asleep again, bam, you wake yourself up. Once again, not very good for you. It's always better to wake up naturally. If you feel the need to hit the snooze button, I really encourage you to go to bed earlier instead of just itching for just 5 or 10 more minutes. Okay, we're coming up on the hour here of this video, but I'm almost done, so let's finish it out. Stick with me. Here is a chart, a graph of what type of sleep and how much sleep people get over the course of their lives. So babies, before they're born, get pretty much 100% sleep, but you can see that even before you're born, you start to be awake, especially in the later stages of being cooking. Sorry, I've suddenly forgot what would be the verb for being what's going on with you before you're born. And you also start to get non-REM sleep, so the stage 1 to 3 sleep. When you're born, you start to spend a lot of time awake, but you also spend most of your day still asleep, right? And so by the time that you hit a couple of months, you should start to get a consistent sleep cycle. So new parents go through this kind of terrible period of time where the newborn babies don't sleep consistently. They kind of sleep at random intervals. And what you'll notice going on here is that this is a bit of a logarithmic scale. So it's not kind of 1 year, 2 year, but as you start to grow up in your childhood, you sleep less and less and less over time. By the time you hit adulthood, you're sleeping right around that 8 to 9 hour mark, ideally. And as you get older and get into old age, you start to sleep less and less and less. But not only are you sleeping less and less and less, you're also spending less and less of that sleep in REM. REM is that good sleep that really improves your body and refreshes you. And you'll notice that over time, as you get older, you experience less and less REM sleep, less and less good sleep. This is one of the things that is most strongly associated to aging. Our brains get dumber as we get older because they are less capable of replenishing themselves through sleep. So one way that we could make ourselves live longer and live better lives is by figuring out how to get that good REM sleep deep into our later lives. This is something that you don't need to know, just like the previous slide, you don't need to know that, but this is interesting. It shows EEG readings of what you look like at different stages of sleep. So when you're awake, your EEG readings kind of look like this. Jittery, a little inconsistent, but for the most part, these are pretty consistent. They're called alpha waves because you're awake, but relaxed. Stage 1 of sleep, you start to get slower, bigger waves. These are called theta waves, these slower, bigger waves, but you're still closer to being awake than not so much. Stage 2, your EEG starts getting a little bit kind of wild, and you start getting sleep spindles, which is periods of really active brain activity, as well as some really extreme spikes in brain activity. Sleep stage 3, you get these delta waves. These delta waves are kind of wild. To give you an idea, this is what you might see when someone's having a seizure. But it also happens when you're falling asleep. Why do these waves happen? To be totally honest, I'm not in full awareness, and I don't know if we psychologists or doctors know that yet, but one of the proposed reasons for this wilder and wilder activity is because it kind of gives your brain an opportunity to reformat itself and clean itself out. Interestingly, from stage 3 we get to that REM sleep, where suddenly our brain is totally calm, about as calm as it's ever gonna get. Weird, huh? Oh, one more thing. So sleep scientists, people who work with not sleep scientists, people who work with EEGs can actually tell if you're falling asleep because you'll start to exhibit some things that look like you're having a stroke, and so they'll do something about it because you might be having a stroke or because you're falling asleep and messing up their study. So, fun fact there. Here's a nice visualization of the circadian rhythm. Remember, the circadian rhythm is our body's internal clock. So it's based on habits and biology and helps keep us on track. And like I said earlier, consistency in your schedule and in your sleep schedule is super important. There are lots of things that get governed by your circadian rhythm. So hunger is one of them, but also body temperature. For example, you may notice that when you're falling asleep you can get hot, but when you wake up it's really easy to be cold, or in the middle of the night it's really easy to be cold. What's going on there is your body is shut down for sleep, so it's not using as much energy and it's not heating up as much as it normally would. The circadian rhythm is really important to be aware of, because if you disrupt your circadian rhythm, you can cause yourself undue stress. So if you're waking up in the middle of the night, if you're staying awake overnight, if you decide to take naps during the day instead of sleeping at night, you can cause stress to your body because your circadian rhythm is working against what you're actually doing. Okay, so we'd ask the question, what are the purposes of sleep? So here are a couple purposes of sleep. I already presented the idea of clearing out waste, refreshing the brain, dealing with neurotransmitters and solidifying memories, repairing your body and growth. When you sleep, you actually burn a lot of fat and breathe that fat out as carbon dioxide. So sleep is great for weight loss as well as for building muscle. Sleep is also something that may have been evolved to protect us. So at night we are vulnerable to predators, and so our ancestors may have benefited from going to sleep in a cave because it kept them away from danger. Okay, sleep problems. So not enough sleep can cause what? Weakened immune system, increased risk for heart, joint, muscle problems, stress, not just emotional stress, but stress on your body, weakened restraint, so you're less capable of making intelligent decisions and controlling yourself, irritability, confusion, brain fog. Not enough sleep causes so much trouble for you. Here's something that is interesting to know. So people who drink on the regular never really get very good sleep. People who drink never really get into that REM sleep. They kind of stay in that stage 1 to 3. The reason for that is that your body needs to concentrate all of its efforts on cleaning up your alcohol spill that happened in there. So because of that, people who drink and have drinking problems, not people who drink, but people who have drinking problems never get enough sleep and can literally become crazier and crazier over time because they're not getting good sleep. So there you go. That's the last slide for this chapter. I hope you found it interesting. I hope it wasn't too dire. The biology stuff is something that not everyone likes, but I hoped to try and make it at least a little bit interesting. Here's all the extra stuff for the chapter. You'll notice that we have a lot of YouTube videos in this chapter. Make sure you watch most of them. You don't have to, but I think a lot of these are super interesting, and a lot of these are the crash course videos that we talked about earlier. And here's your vocabulary for week 2. We've got a lot of vocabulary in this chapter, so make sure that you go ahead and do this week because it's probably going to be a big part of your test. Okay, so hope you enjoyed this chapter. I enjoyed putting it together for you and making the video, and I really hope you have a great day.